Welcome back, ladies and gentlemen. In this video we're going to be looking at Newton's law of universal gravitation. We will also consider how gravitational attraction works between masses that are sort of considered point masses, where the size is quite small, and also where gravitational attraction works between large objects like astronomical size objects, Earth, our moon, the sun, as some examples. So gravity, of course, one of the many things Newton did was sort of figured out how gravity works, and he did this over 300 years ago, which is kind of amazing. What he realized first was that an object in orbit like the moon, it really is acting in a similar fashion to an object that would simply be dropped and fall straight toward Earth's surface. What Newton did, he had a couple thought experiments he was looking at, and an easy one to sort of visualize is, let's say you have a low hilltop, and on this hilltop you have a cannon. All right? And from this cannon you're going to shoot cannonballs. Various amounts of gunpowder will allow you to produce various ranges. So the cannonballs are launched horizontally, and we get the projectile motion happening, parabolic trajectories, and with larger and larger initial horizontal velocities, we get greater and greater range. And this is all well and good, and Newton would have recognized this also. But he took this a step further, and he looked at this on a larger scale. And what he thought about was, well, let's say if I could picture the entire Earth. So here's my poor attempt at Earth with a hill on it. And from the top of the hill, we have the cannon. We're going to launch some cannonballs. And it's not reasonable, of course, to look at a cannonball as traveling a significant portion around the globe of Earth. But this is just a thought experiment, and this is what Newton was trying to reason out. If you launch horizontally, and typically the cannonball is going to fall and land on the surface, but then if you increase the initial velocity, it's still a horizontal launch. But what's going to happen is it's going to take longer to fall, because the surface is curving away from that initial trajectory. So as it falls, the surface moves further away, and you end up getting greater range. It lands further from that hilltop. And with greater and greater initial velocities, Newton was figuring out that it would travel further and further around Earth's surface. Now, my attempt at this diagram is very poor, but you might be able to see with a large enough initial velocity, terrible there. With a large enough initial velocity, what would happen is the ball would be falling and being pulled down by Earth's gravity, but the surface is falling away from that trajectory, and it turns out at some important initial velocity, it's going horizontally fast enough to continually miss Earth's surface, and would end up coming back to the hilltop, back to the cannon. And in theory, in a super simple, unrealistic world, it would actually blow up the cannon itself. And it would be moving in a circle. So you have circular motion here, and the circular path is produced by a force toward the center of the circle, right? You can recognize that. That's your centripetal force. But there's more to this, and I want to show you a different diagram, a better version of this diagram right here. So check this out. This is actually a copy of one of Newton's original diagrams that he published, and it's not exactly easy to see. It's not exactly perfectly clear, but you can recognize a few things. You can see a hilltop from location V, and you can see various short trajectories. There are letters here, D, E, F, G, And with a larger and larger initial velocity, you see the greater range. With enough initial velocity, you see this circular pathway, I believe is labeled B, here around Earth, and it just comes back to where it started. And if there was nothing to interfere with the speed of the cannonball, for example, it doesn't get bonked, it doesn't bump into the cannon and explode or anything like that. Nothing is interfering with it. There's no atmospheric drag or anything else. It would actually continue forever, going in that circular pathway. But you could achieve a different circular pathway, which is further from the surface. And if it's going to be a circular pathway, all you need is a velocity tangential to the surface, tangential to that circle, and that velocity simply has to be large enough. And with a large enough velocity at a particular radius from the center, we'll have a radius r. That might be hard to see, but there it is. There's radius r. So for that radius and a certain velocity, it would maintain the circular pathway. It would have just enough centripetal acceleration to change the direction of the velocity. But there are other types of motions as well. And for example, if we go back to my poor attempt at this, if we launched this cannonball from this hilltop with a large enough initial velocity, it's going to shoot out further away from the surface, further away, but then gravity will gradually pull it back, pull it back, pull it back. And what you're supposed to end up with is actually an elliptical orbit. The radius from the center of Earth actually changes. And with an ellipse, if you recall some geometry, an ellipse actually has two centers. And the two centers are some distance apart. And what's interesting is the ellipse actually is orbiting both centers. With the ellipse is orbiting, the cannonball moving along this elliptical path can be thought of as orbiting the two centers. Now, what happens as the centers of an ellipse get closer and closer together, and eventually, if the centers coincide, so you would get a rounder and rounder. That one was terrible, sorry. And finally, end up at a circle. And the size doesn't necessarily shrink like this. I'm just trying to quickly illustrate a point. That a circle is really a special case of an ellipse where the two centers coincide. So it is possible to have a circular orbit, but it is also possible to have an elliptical orbit. It turns out the orbits of the planets are generally elliptical. They are not circular. But for most of them, the orbit is circular enough. It's close enough to a circle that we can do a lot of work with the orbital motions as circular pathways. It makes it a little simpler for us. Okay. So in this situation, all we see is a greater and greater initial horizontal velocity leads to greater and greater range. And on a sort of a local or regional scale, this is fine, because on a local scale, the surface can be thought of as relatively flat, barring any hills or valleys. But on a larger scale, if we can envision the entire Earth, Newton realized that the horizontal launch, if it were fast enough, would allow the projectile to completely miss Earth as it fell. And it would be considered orbiting the Earth at that point. And Newton's part of Newton's genius was that he realized this is precisely what the moon does. We have the Earth and we have the moon, and the moon is orbiting Earth. An orbit mostly circular. It is not quite circular. But as the moon travels in its orbit around the Earth, it is falling toward the Earth. It is just not getting any closer to the Earth. It's completely missing it. And that's because its speed, we could say its speed, as it travels is just fast enough to sort of keep it out there, but it still has this centripetal force and therefore centripetal acceleration toward Earth's center. All right, and so good job, Newton, for figuring that out. Now, regarding the actual mathematics of the law of gravitation, I really ought to say the universal law. Of gravitation. And the reason is it is universal. It is applicable to any object in the universe, essentially. The equation is quite important, quite famous. The force of gravity, or a force of attraction, acting on some object, is equal to a quantity, capital G, multiplied by the mass of object 1, multiplied by the mass of object 2, and divided by the radius or distance between those two objects. Now, mass and radius is a distance. That's easy. This G, this is called the gravitational constant. And its value is actually quite small, 6.67 times 10 to the negative 11. And its units are going to look a little strange, and the units are simply such that they will allow conversion of this is going to be kilograms squared divided by meters squared, conversion of these units into newtons to make this equation work out. So the units here become Newton meters squared divided by kilograms squared. And when the units are all worked out, you can see that the meter squared will cancel and the kilogram squared will cancel, and you're left with newtons, measurement of force. So how does this look? You essentially are going to have a mass there and a mass there, M1, M2, and those masses are some distance away from each other. That would be the radius. And there is a force of attraction between those two objects. And the force of attraction acts along a line straight between those 2 point masses. So here's F there, and here is F there. And what you see right away, I hope, is first of all, the two F's are equal in value. They act on opposite or different objects, and they're acting in opposite directions. So equal, opposite, acting on different objects, that's a force pair right there. So we have Newton's third law shown right here. And there's another way to think of this. I mean, we first learned that forces always occur in pairs, but you might start to shift that thinking. It's okay to continue to think of it that way, but look at this. Without one of these, you don't get the other. You cannot have just a single force all by itself in the universe. And in fact, you might think of the two forces really as just one force. One force that is somehow these two objects are interacting with each other in some way. In terms of this particular instance, it's gravitationally. So the gravitational interaction creates a force. And that one force has one value that you'd figure out, and that one force is affecting each object differently. That one force is producing an acceleration, or would tend to produce an acceleration that way for this mass, this way for this mass, acceleration of object 2, object 1, and the accelerations might very well be different values because the masses would be different, or could be different, right? That's generally how this universal law of gravitation works. And again, got to say universal because this constant works universally. It is a constant, literally, it doesn't change. So you could figure the force of gravity between two stars, between two planets, between a space shuttle and a planet, between a space shuttle and an astronaut, between a guy walking his dog on the beach and the dog that he's walking. There are two masses, there's a distance between them, there's a constant here, and you can work out a force of gravitational attraction between a man and his dog. Wow. So, that is generally the universal law of gravitation. So it shows what's an interesting relationship, though, and this really is something that's going to come up on tests, particularly the AP exam. There's something called an inverse square relationship, and you have likely seen this elsewhere. Okay, so we're sort of delving into this equation. And this inverse square relationship is simply that the force of attraction will vary depending on the inverse of the square of that radius, that distance between them. So that's your inverse square relationship. The symbol here I want to use is not, of course, not an equal sign. Oh, goodness. Bit of a brain fart. Sorry, guys. Looking this up real quick. Handy dandy textbook. Oh, it's not showing me. Well, proportional to, is this proportionality? Yeah, you get the idea. Sorry about my lack of clear thinking on that symbol to use. But you see that as the distance between the two objects is going to increase, the force of attraction will decrease. And more specifically, if you double the radius, what happens to the force? The force would actually be 1/4 the value. If you triple the radius, then what happens to the force? The force would be 1/9 the value. So it's this inverse square relationship in evidence here, right? Not that way, this way. So that change leads to this result. That change leads to this result. So there's more, though, and it's possibly obvious to you, or you hear it and you might say, well, of course, that makes sense. And finally, it is that if you have an object being acted on by multiple other objects, so here's M1, here's M2, and let's say here's M3. So we want to know what is the net force acting on M1, right? Well, all we really have to do is figure the force of attraction acting on M1 caused by M2. So we have to find this force, which also shows up here. And we have to find this force. This is force of 2 on 1. We must also find this one, which also shows up here. This is force of 3 on 1. And all we have to do now is take a look at that object by itself and say, well, there are two forces acting on it. What is the vector sum of those two forces? And so I can sort of visually show this. I'm going to have a force this way. I'm going to have a force this way. And sort of a visual way of doing this is to make that parallelogram with those parallel sides. And the resultant of those two forces, when I combine them, it's going to go in this direction. And I can redraw the whole thing to be a right triangle quite easy. There's one. I'll try to get it reasonably accurate. There's another one. And so, of course, my resultant is here. So this is going to be F net. And I have a right triangle. I have a right triangle if these two are at right angles to each other. Forgive me. If it's not right angle between those two forces, that's okay. We can still work it out, but there's a few more steps. But it certainly is possible. We understand how to work with vectors, and I'm not going to go into all of that right here in the video. That's a pretty simple matter, just crunching some numbers. So to boil this down, if you've got multiple objects affecting one object, you simply must find the vector sum of all of those forces in order to find the net force acting on that object. Piece of cake, easily understood. Well, now, we've been looking at those objects as if they are point masses, relatively small. An astronaut, a man on the beach, even the space shuttle, relatively small compared to a planet or a moon. So, how do things change spherical bodies? If we're talking about large astronomical objects, so we're going to deal with spherical bodies, and it turns out there is almost no changes we have to make. So, if here is Earth, well, there's a center of Earth, and we have some object, call that object mass m, and it's some distance away from Earth. Okay, this is interesting though. All we have to do is consider all of the mass of the Earth concentrated at the center. I'll call this capital M for mass there. And the reason is this, real quickly. This mass is going to be affected by part of Earth here, and it's going to be sort of strongly affected by that one. But it's going to be affected by the part of Earth here in a weak way. And it will be affected by part of Earth here and here in relatively equal ways. And if you were to sum up the effects on this object of all the little bits inside of Earth, it turns out it is equal to treating Earth as having all of its mass concentrated at the center. So that's nice, because what we can do is figure out a distance from the object to the center, and that's our radius that we will use in our calculation. And so we know a mass, we know a radius. We could still find the gravitational attraction between these two objects quite easily. So essentially what we're doing, M and M, is we're doing this. We're treating Earth or any other spherical astronomical sized body as if it were a point mass. And we do the same exact calculation. F equals G M over R squared. Not a problem, right? And you can see it generally is going to be a pretty easy calculation to do, although some situations you want to be aware are going to ask you to think on your feet and recognize a few little tweaks that you've got to do. So, check this out now. From this equation that we have, what if we had an object sitting on Earth's surface? Yeah, let's take a look at that. Whatever that is, a box, a house, a car, it doesn't matter, but some object on Earth's surface. Then the radius is going to be, the radius that we use in our calculation is going to be the radius of Earth, isn't it? So we can sort of look at this situation, and we will have the force of gravity acting on that object. For this gravitational constant, we have mass of Earth. We're going to get a little more specific. We have the mass of that object. And now this radius is radius of Earth. This is generally how you'll see it written. Just capital R with a subscript E. And so we could find how strongly Earth is pulling on this object at our surface if we knew some of these values, right? But we also know that the force of gravity affecting an object is equal to mg, the mass of that object times gravitational acceleration due to Earth's gravity. What about combining these? Because it sure seems it's going to produce the same answer. And it's interesting, we can definitely do that. I'm going to rearrange this and pull m out of there, and we get g times mass of Earth. Ooh, I forgot something. Squared. Don't forget your exponents. Radius of Earth squared. And I'm going to equate that to mg. And you can see pretty clearly that that little m cancels out, no big deal. And we're going to be able to see that the gravitational acceleration on our surface is equal to this gravitational constant, mass of Earth, divided by radius of Earth squared. And when you look those numbers up, they are provided in your textbook. They're not numbers you need to memorize, but when you do the math, it turns out you get 9.81 meters per second squared. It works out. So it's quite interesting. But also using this kind of calculation, look, this is kind of a special thing right here. This is the acceleration due to gravity specifically at Earth's surface. If you have an object away from Earth's surface, then you're still using the mass of Earth, but you must change the radius that you use in your calculation. And so the radius there is going to be radius of Earth plus some other altitude, right? Plus some other distance, lowercase r, whatever you like to use. But using this type of thinking, we can find the value of gravitational acceleration for any object at any distance above Earth's surface. And in those cases, we would simply have to say that the radius we use in our calculation is greater than the radius of Earth. And we just have to recognize, well, how high above the surface is it? We have to add the radius of Earth and simply perform our calculation here, and we can find a new value at that specific location. All right. Thanks for watching. Please read these sections in Chapter 12. You're going to get some great insight about this. And let me know if you have any concerns. See you next time.